morning, everyone, and welcome to this session. My name is Thorsten Jacobs. I'm a solution architect at Databricks. Shortly about me, I'm working based out of Stockholm with customers mainly in the Nordics. And before Databricks, I used to work as a data science consultant, and actually I'm a physicist from the start, so I did my PhD in Stockholm. Today I want to talk with you about common struggles that companies have when they move the data to a data lake and they want to use that data for their machine learning and their analytics use cases. And I have helped a lot of customers migrating to the cloud, to a lake, and we see common challenges that they have. So I want to point these out and how you can appoint them with a concept called the Lakehouse. And then I also going to talk a bit about Databricks and how we achieve this Lakehouse architecture. And in the end of this session, I try to answer some of the Q&As if there's time. Otherwise, you can also go to our Databricks booth and ask some questions there, or we will get back to you afterwards. So first, let me start to introduce Databricks. We are the data and AI company. It's a platform fully cloud-based, and we have thousands of customers around the globe and believe in open source, believe in the cloud, and are the original creators of a number of very popular open source tools. And the most famous one might be Apache Spark. So the founders of Apache Spark, when they invented it around 10 years ago now, then later created or started Databricks. And we have customers in basically all kind of verticals, small and big. And there's a number of these here in the list are also talking at this summit, I see. And basically it proves that, I mean, we are industry proven, work at scale. Some of our customers really have petabytes of data they're working with and thousands of machine learning models. So it's a reliable platform. And actually half of all Fortune 500 customers nowadays use Databricks. Clearly, like being more data-driven, using AI is a large strategy for many companies nowadays. So the majority of all CEOs say that AI is a strategic priority, and there's like tremendous business value in this. However, what we also see is that a lot of these, like the majorities of these big data projects and of data science projects actually fail or never make it into production, never create any business value. And I'm gonna try to explain a little bit why that is, or what some of the challenges are. So let's basically talk about different data platforms that are common and how they evolved. The classical one has been around since centuries, is the data warehouse, where you save structured data in a format that is basically predefined. So you have a number of tables that are connected to each other. The warehouse then optimizes this, and it's very fast for BI types of queries. You usually use SQL to run these queries. And here are a number of examples of popular warehouses. The advantages, as mentioned, is like these are very good and proven fast tools for your BI applications. However, they work in a limited way for machine learning, and the reason for that is that they mostly support structured data. You have to basically do your ETL, your extract, transform, load, before loading it into a format that fits into the warehouse. They mainly work with SQL, and a lot of nowadays machine learning frameworks are based on some open source tools that use other languages. Or so basically you're a bit limited in the tools that you can use and the data you can import into this warehouse. Then the data lakes came up just for this reason, because they are very flexible when it comes to what kind of data you can save in them. You can, from structured, semi and unstructured data, they basically support everything. It's just a large like a place where you can just dump all your data. It's very flexible what kind of tools you use on them, because they save the data in the like flexible original formats. And this is commonly then used for machine learning. However, so as mentioned, it works well it works for these machine learning use cases. It's an open format. It's a very large ecosystem of tools that can be used. However, the support for BI type of workloads isn't so perfect. It often is a bit slow, or you simply don't have the structure in the lake that you need. And there might be some data quality problems, basically making these lakes more of a swamp where everything is dumped, and in the end you don't know which kind of files are, and if you have corrupted files, etc. And that gives some problems with the data quality. And this is basically what it looks like, that in larger enterprises or in enterprises, you basically have these siloed stacks of different data solutions. You have the warehouse still used for your BI solutions. You have the lake where some engineers might do like an ETL kind of operations to prepare data for your lake or maybe for your machine learning. Then you have the machine learning part where you do directly on the lake. If you then want to do streaming with like live type of data, you might need even other tools and engines to basically support that. So in the end, you end up with a lot of different tools, frameworks. You have to connect them together. You have to know how each of them work. You have to shuffle around data. Maybe the data scientist might want to use some data from the warehouse. So you have to create a copy so that this data is ready for machine learning. Have to take care of these copies. You maybe want to use some of this streaming part, and then you have this kind of lambda architecture where you have two paths, like one of the batch data, one of the streaming data, and you have to take care of both of them. And basically this creates like walls between different groups, makes it difficult for them to collaborate, and you don't really have this one source of truth or one platform that you use for your data, and add a lot of complexity. And this basically leads to a lot of troubles. For example, if you want to do analytics, if you want to do machine learning, just getting the right data, knowing which data you have, relying on its quality, and basically being able to use the right tool for your use case. And to simplify this, I think it was basically Databricks who came up with the Lakehouse term. And now we see a lot of our competitors basically using the same term. And the idea here is that you combine the best of a lake and a warehouse. So basically having one layer of like source of truth for your data, which is reliable, and one platform for all your use cases. And in this case, basically you take a lake as a base, and then you add some of the kind of lessons learned and advantages from a warehouse and combine them together. So this is what I mentioned we call the Lakehouse, that we have basically one platform for all your data use cases and your data needs. And a key component of this is the Delta Lake, or the Delta format, which is another open source format that was developed by Databricks. And it basically adds a layer of governance and performance on top of your existing data lake, and gives you like better reliability. It makes it faster and helps you with your data governance and scaling. And first, let me address some issues that often occur when using classical data lakes. There are a number of problems from the data engineering side, especially if it comes to, for example, appending or modifying data. If you want to simply delete a row from, say, a CSV or Parquet file or something, what you basically have to do is you have to create a copy of this that does not contain the data, the row that you want to delete, and then delete the old version because it doesn't natively support these modifications of files. You might have jobs where any kind of workload is failing. This can always happen. However, the problem might be that once the job fails, it might leave corrupted data on your lake. So in the end, you don't know if you can rely your files anymore, if they have been corrupted by some failing jobs. Real-time operations, the streaming I talked about, is also quite a complex structure then to align both your batch and your new live streaming data and have them updated at the same time. And you might want to keep old versions of your data, and basically, if you do any changes, you just want to be able to easily revert and make sure that that you can just go back to the old version. You maybe want to handle metadata. So you need some sort of metadata to understand what kind of data do I have in my lake, where is it? And then once this data becomes like more and more larger, also this metadata handling might become a problem. And if you have lots of small files, especially for machine learning, think of having like 100,000 of like say image files or something, they might get hard to handle. It might lead to performance issues, and generally also like there might be issues with security and data quality. So if we group these kind of challenges, we can basically say they're related to reliability, to performance, to data governance, and to data quality. And that, of course, then also on the business side, you might have projects that simply fail because the data you have is not reliable enough, or you don't find the data you need, you don't trust it, leading to like poor productivity and also like risks for both security, but also for basically the performance and results of your analytics or your machine learning use cases. And then what Delta does basically is you put it on top of the existing lake. So it's basically a layer on top. And this layer then adds like reliability, performance, governance, and quality. So it addresses these common issues. And it's based on an open format, on a Parquet format. So for those of you who are used to big data in the lake, then you might probably be familiar with Parquet. And basically it makes your data engineering easier, and by having a now curated data lake. And similar to what we maybe know from warehouses, the concept here would be that what we call the meta-long structure, that you ingest your data in a raw format, basically without doing any ETL, so you still have that later on to rely on. And then you successively save it in new tables and increase data quality by doing cleaning, augmentation, aggregation, and so on. And this is maybe similar to from a warehouse you might know as a staging area and data marts. So the concept is the same, and then helping you basically to find your data and to organize your data inside the lake. And so how exactly does it address these issues that I talked about earlier? We add asset transactions, something that you might know from a data warehouse or a database, indexing and caching, basically access controls for tables, and for the data quality, you can set expectations to your data. So this data, for example, this column should be within this row, otherwise there might be within this range, otherwise there might be a problem. Or you can also set expectations to your schema and say if you insert new data and this should be an integer, but you try to insert a different format, then it might bring up a warning, simply to assure the quality. And yeah, basically what this does is to take this kind of lessons learned from warehouses, like asset transactions, indexing, etc., and then apply that to a data lake. And this will ultimately improve the quality and improve the productivity and also like total cost of ownership. You don't have to handle all these problems all the time, but just can rely on the data that is in your lake. Let's look a bit under the hood what Delta actually is. As mentioned, it's an open source format, so you don't need Databricks for Delta, and it's based on open source, or like an open format called the Parquet format, and it would all of the data would be saved in your lake. So you take, say, ADLS or S3 in AWS or blob storage or whatever, where you might have your raw data, and then you can use Databricks to save it in a Delta format. And under the hood, it will basically create Parquet files together with transaction logs and indexes. So this is what is then stored on the lake. And inside Databricks, you will then have Delta tables. So basically, you get a like data access in a metadata store with databases and tables. Simply, specifying where you want to save it, like with a few lines. If you already know Parquet, it's very similar than using Parquet. And then this is where also the access control happens, where you can basically say, okay, this user groups should have access to these kind of tables, etc. And the third part is then the Delta engine. And the Delta engine basically uses these files to achieve all these features that I was talking about, like these asset transactions. So asset transactions basically making sure that if you have someone reading your data while at the same time you want to write it, then it makes just sure that each of these transactions happens after each other, and there's no like no error or no problem since several instances try to access the file at the same time. It's simply just assuring this quality. As mentioned, schema enforcement to also ensure your quality. With Delta, you can do upserts, so updates, inserts, deletes, also something that you might be knowing from a data warehouse or a database, and that classically you cannot do with a data lake or with Parquet formats, and it basically adds these functionalities. What we call time travel is the functionality of basically saving each transaction that is done on the table, and then you can go back to the previous versions of it. You can also see what was done exactly. And then there are also some goodies that we keep only for Databricks customers. For example, like file compaction, Z-order partitioning. These are like performance-related features to basically make Delta faster when running your queries, etc. So this is basically what Delta is. And as mentioned, it is open source. So there are a lot of connectors available. There is possibility to, for example, write to Delta Lake directly from Azure Data Factory or read it with Synapse. There is a standalone reader that doesn't need any Spark. And so it's still somewhat new, so it's evolving, but more and more like connectors are coming, supporting Delta and making sure that you don't lock in your data to a certain vendor, that you can always choose the tool that you want to, or always migrate elsewhere if you want to. So basically making sure that your data is yours. And this is then what the platform basically looks like, where you have the Lakehouse platform, where you have an open lake, a data management layer on top being Delta. This lake supports all kind of formats. Databricks is on all major clouds, and you can basically have the same experience from all these clouds, and then use the platform for all your work like use cases. And if we look at, for example, data science workloads, we have inside the Databricks workspace, you usually work in notebooks, something that data scientists are very familiar with. These notebooks support multi-language, Python, Java, R, Scala, and in the background, you have the Spark engine doing your executions on your data. However, you don't need to run no Spark to use Databricks. You can also just use vanilla Python or something. And another thing that is not shown here is also that you can use SQL. And you can all use all these languages within the same notebook, just switch within the notebook. They are collaborative, so a bit from what you're known from maybe like Office 365 or so, where you can co-edit in the same notebook, where you can add comments to easily share it to collaborate. And then here in the workspace, you have all your access to all your data, to your compute. You can automate with jobs, etc. As mentioned, we can use Python, which is very popular for data scientists. You can use Spark. The problem with Python or one thing with Python is a lot of data scientists like to use pandas for their data wrangling. However, pandas is a tool that works only basically on one core of your machine, and everything is in memory, so it's not very scalable. Once you reach the limits of your machine, then you can't scale out easily. And for those who want to scale but don't want to learn Spark, we developed Koalas. And Koalas is basically a tool that is designed to look like pandas. You just say import Koalas as KS instead, and then you basically have a Spark cluster in the background doing your compute in a distributed way, and that makes it much easier to scale up while not having to learn so much new code. And we saw that for example, Virgin Hyperloop, they wanted to had problems when scaling up, and they didn't want to learn Spark, so they started with Koalas. And now what you can see here, if you have larger data sets starting from about 1 million rows or something like that, so really nothing too big. I think a lot of companies have that. You can have quite some performance increase using Koalas or Spark. And in this case, with Koalas, they only had to do 1% of changes in their code. The next use case might be the machine learning use case, and the data scientists or machine learning engineers. We offer basically automatic tracking of all runs. So whatever experiments you do, they are tracked in the background, and you can easily then recall the results and the model. There's a central model registry, which makes it easy to save and share your model with a one-click option to deploy it as a REST endpoint. So making this setting it into production quite easy. And also using Delta and this time travel functionality, for example, it also makes sure that your runs are reproducible. You can not only go back to certain versions of your code, but also go back to certain versions of your data to reproduce this run. And so this is what it looks like a bit under the hood. We have special run times for data science, which comes with a number of typical packages already pre-installed, like scikit-learn, TensorFlow, etc. So you're just ready to go without having to install anything. As mentioned, with options for scoring your model. The MLflow framework is another open source tool developed by Databricks, which allows to basically track your whole data science life cycle, and also helps with setting it into production. There are more options for doing AutoML. So basically the whole end-to-end data science and machine learning workflow is supported. That was also recognized by Gartner, who puts us in as a leader for data science and machine learning platforms, now the second year in a row. And the next part, so I talked about, okay, how do we save our model, our data in a reliable and a central place? Then how do we use this data for our machine learning and data science use cases? And now the next use case might be the BI users who want to use SQL, who want to use dashboards, create reports that way, maybe have alarms and so on, who don't know much about Spark or don't want to care about clusters, etc. And for this, we have the SQL Analytics workspace. It's currently in a preview state, where you basically have fully supported SQL. You have endpoints that you can connect to other BI tools if needed, like Power BI, Tableau, etc. And this enables you to do SQL on your lake. So on all the whatever data formats you have, the semi-structured, unstructured data, you can now run SQL, and basically using Spark in the background without even knowing that you use Spark, simply by using classical SQL queries. So just to summarize, what are the key properties of a Lakehouse architecture? Basically, it should be simple. You want to have ideally one platform, or at least as a few different tools as possible to handle in your architecture. It should be open so that you basically don't lock in your data. So you're ready for the future. You're ready for the next big open source tool that will come and is like usable for your machine learning needs. So based on open formats, and also allowing you to basically work on different clouds, because that's also a very common strategy nowadays, that the companies who use different clouds, and that you can easily that data teams easily collaborate, that you don't have the silos, but they all can easily share their data and their models, etc. And just to show again how the Databricks platform leverages this. So we have this one platform for all your data, all your use cases. So basically making it quite simple to use, assuring that you can use the language that you use to, like Python, SQL, R, and etc. Then it's an open platform. As I said, we strongly believe in open source. The tools that were developed by Databricks have now 1 million monthly downloads, and have like quite a large adoption. And addition to that, we also have a number of partners, like hundreds of partners in the data landscape, where you can connect to the Databricks platform, where they help to migrate data from one platform to Databricks. So they're like native connectors, for example, for Azure Machine Learning, for Synapse, etc., where you can connect to. And it is easy to collaborate, like different roles can share their notebooks, their code, their data sets, and their machine learning models within the same workspace or within the same platform, and making sure that you don't have these kind of silos. In addition to being a data platform, we can also help you with your projects. Another large problem why a lot of projects fail is basically that companies don't yet have all the knowledge. So we can help with basically setting projects to production, with teaching the data team how to basically both build a platform, but also how to use it, and have different services and offers around that. So that's all I wanted to say. Thank you. I hope it was helpful. And as mentioned, if you have any questions later on, you can also check out our Databricks booth, or I think there will also be other sessions or roundtables from colleagues of mine at Databricks. And another thing I can announce maybe quickly, next week we will have the Data and AI Summit, which is free and online. If you want to know about Databricks, you can check that out as well. So thank you, everyone, and enjoy the rest of the conference.